All right, this is a video lesson for lesson 4, which is the multiplication rule with complements and conditional probability. So this is a continuation of the last lesson, but looking at more advanced applications. These aren't necessarily the longest, hardest problems, but they're a more sophisticated rule or a more sophisticated way of using some of the ideas of the multiplication rule. And other things we've learned throughout the semester. So the first formula, there's two big formulas we're going to learn in this lesson. The first one is right here, the probability of at least one of something occurring. So let's say, for instance, we were trying to figure out the probability of at least one ace occurring in whatever situation. We're trying to pull cards and we're looking for the probability, maybe we're pulling 10 cards, and we're looking, what's the probability of getting at least one ace in those 10 cards? Well, here's what we're going to do. Let's just take a look at what that situation looks like. We could get 0 aces, we could get 1 ace, we could get 2 aces, we could get 3, or we could get 4. Now, I don't even know the rules of this. I don't know how many cards I'm pulling or anything, but I do know that this covers all the number of aces I could possibly get, because the most aces I could get is 4, the least aces I can get is 0, and everywhere in between is accounted for. Now, if I were to take all of those probabilities and add them up, it should equal 1. If you take every possible outcome and add them all together, you should always get 100%. So all these things should add up to 1. Well, if we are talking about at least 1, that's referring to 1, 2, 3, or 4 aces, because that's the max is 4. So this is the at least 1, all of this. So another way to write this is the probability of 0 plus the probability of at least 1, that means at least 1, equals 1. And if I subtract over the 0, now you're seeing where this formula comes from. The probability of getting at least 1 of something is equal to 1 minus the probability of getting none of it, or 0 things. Okay? And this is a really powerful formula. We use it in a lot of ways, and we're going to see that right away. So here's a problem. It says if a couple is going to have 6 children, what's the probability that at least one of them are boys? So probability of at least one boy. It would take us a while and be a little bit complicated to figure out the probability of 1 boy, 2 boys, 3 boys, 4 boys, 5 boys, all the way up to 6 boys. That would take us a little while. Instead, we're going to use this formula. We're going to do 1 minus the probability of no boys. None of them are boys. Okay? Well, that's still a complex situation. It still involves multiple probability, multiple events. So we're going to have 1 minus, well, what's the probability that the first child is not a boy? Well, that just means they're a girl, so 1 out of 2. Well, the second child not being a boy, that's also 1 out of 2, because the first child didn't affect the second child. Then the third one not being a boy, that's 1 out of 2 again. Whoops, sorry, 1 out of 2. And we'd get 6 of these. Instead of doing that, we're just going to write 1/2 to the 6th. So 1 minus 0.5 to the 6th. And I could type that into my calculator. 1 minus 0.5 to the 6th, which is 0.984. So this is the probability that at least one of the 6 kids is a boy. So this is a different gear. We're going to change gears here and look at something else as we work towards another formula that we need to learn today. Okay? They ask us, what's the probability that a person tests positive given that they lied? So when you say that, when you say given that they lied, we know we're talking about this group of people. These people didn't lie, so we're not talking about them. We're talking about the liars. Okay? These liars, and we're assuming we're testing a lie detector, out of the 51 liars, 42 of them tested positive. So the probability that somebody tested positive given that they lied is 42 out of 51. There were 51 liars, so given that they lied means we're only talking about the liars. So there were 51 liars and 42 of them tested positive. That probability, going to the calculator, is 0.824. And that's our answer. Now, that was done logically. Not all problems can be done that logically. You don't always have a table. You can't always figure it out. So we need a formula for this. And this is the conditional probability formula. So we learned 2 formulas today that need to go on the cheat sheet. This is the second one. Okay? And this actually comes from the multiplication rule. I'm just going to write this down here so you can see it. The probability of A and B equals the probability of A times the probability of B given that A has occurred. That's the formula we learned in lesson 3. Well, if you just divide both sides by probability of A, then you get this formula up here. It's just written backwards. Probability of B given A equals probability of A and B over probability of A. The way I talk about this is I say the probability of B given A is equal to the probability of both over the probability of the given, A's being the given. So that's the way I remember it. Probability of both over probability of given. So let's do an example of this. You might not be able to tell right away that they're giving an example of this by the way they word it, but we have to kind of figure that out. They say, what % of those who pass the first test also pass the second test? I always skip to what the question is. There's the question that I just underlined. So we're saying, what % of those who pass the first test? That's the given. We're accepting that they passed the first test. So it's given that they passed the first test. That's accepted. We're accepting that they passed the first test. We want to know how many also passed the second test. So we want to know who passed the second test given that they passed the first test. Well, we're going to do the probability of both. So probability of passing both tests over the probability of the given, meaning pass the first. And that information's given here in the question. They say 25% of the class passed both tests. So that's my both right there, 25%. They say 42% passed the first test. That's the given. So 42% passed the first test. And now I'm just going to divide. And it comes back as 0.595. Now, the way they worded it, we actually aren't going to give this as a probability answer because they said what %. So I need to convert this to a percentage, and that's easy. 59.5% of the kids that passed the first also passed the second. Normally, we would give it as the decimal, but they asked for a percentage, so we gave it as a percentage. Okay, from here on out, you can practice these and then go back to the video and see if you got them right and check off of what I did. But now it's up for grabs. It could be an at least one question or it could be a conditional probability question. So you have to kind of decide. So this first question I'm reading says, I'm kind of skipping to the question. It says, what is the probability that a student takes Spanish given that the student is taking technology? So it's a conditional probability question. Probability of Spanish given taking technology. Well, that's going to be the probability of both, so somebody that's taking Spanish and technology, over the probability of the given, somebody that's taking technology. The probability that a student takes technology and Spanish, there's your both, 0.087. The probability that a student takes technology is 0.68. That's your probability of the given technology, 0.68. And with that, I'm ready to solve. I'm going to take 0.087 and divide it by 0.68. And I get an answer of 0.128. That's it. We just need to know these two formulas. So now the second question says, what is the probability of getting at least one? That tells me it's an at least one problem. So immediately I'm going to go to my formula. Probability of at least one question being right, because we're talking about multiple choice answers, or multiple choice questions getting right. So the probability of at least one being right is equal to, let's make this a 1 so you don't think it's conditional, at least one being right, is equal to 1 minus none, which the probability of none would be no Q's right, getting nothing right. Okay? Well, the probability of getting no questions right, I'm going to do a little bracket so I can figure this out. Well, what are the chances I get the first question wrong? Well, there's 5 answers on the multiple choice question, so that means I have a 1 out of 5 chance of being right. So the probability that I get it wrong is 4 out of 5. I have a 1 out of 5 chance of getting it right. That means there's a 4 out of 5 chance of getting it wrong. Well, isn't it going to be the same probability for question number 2? 4 out of 5 are wrong, are right, or sorry, are wrong. Okay, then again for question 3, and again for question 4. So there's a 4 out of 5 chance I get each of the 4 questions wrong. So now collectively, what's the probability that I get all 4 of them wrong? Well, I can, instead of writing it like this, I could just call it 4/5 to the 4th, since there's 4 questions that all have the same probability of getting them wrong. Okay, so 1 minus 4/5 to the 4th, and I'm just going to go and type that right into my calculator. I don't really need these parentheses at this point. I can get rid of them if I want. They're not really doing anything. So 1 minus 4/5 in parentheses to the 4th is going to be 0.590. So there's a 59% chance that I'm going to get at least one question right. Just a couple more examples. Again, it helps to just skip to the question. What is the probability that a teenager owns rollerblades given that they own a skateboard? So the probability of rollerblades given that they own a skateboard. Well, the formula says probability of both divided by the probability of the given skateboard. So now let's actually read the facts. 48% of all teenagers own a skateboard. So the skateboard number is going to go on the bottom, according to our formula. 48% on the bottom. 39% own a skateboard and rollerblades. That means both. So 39% goes on the top. Divide it out. We get 0.8125, which I'm going to call 0.813. And that's it. So all these problems boil down to picking the right formula and then just going and finding the information that satisfies that formula. So one more question. A company tests a batch of altimeters without replacement. That's key, without replacement. That means we're not independent, so probability is going to be affected, to see if they are acceptable for distribution. If one altimeter is faulty, then the whole batch is denied. Given that 3% of altimeters are faulty, what's the probability that a batch of 400 altimeters will be denied based on the first 2 items selected? Okay, a lot of words here, a lot of information being spewed at us. Okay, we're looking at the probability that it's rejected. Right? It says it's a probability that a batch of will be denied, rejected, denied, whatever. Probability of denied. Well, to get denied, that means that one or more of the altimeters are faulty. Okay? If both are faulty, they're definitely going to deny it. If one's faulty, they're going to deny it. They both have to be good to not deny it. So the probability that it's going to get denied is equal to the probability that at least one is faulty. I hope that makes sense. Okay? The only way we're going to deny it is if one of them are faulty. Okay? So that's going to be the probability that at least one is faulty. Well, that would be equal to 1 minus the probability that none of them are faulty. Well, there's only 2, so that neither one is faulty. Well, that means they're both good. So 1 minus the probability that they're both good. Well, what's the probability that the first one's good? 3% are faulty. What's the probability that a batch of 400? Okay, well, I got to figure out what 3% of 400 is. Okay, so I'm going to take 400 times 0.03. That means, so right here, 3% are faulty. That means 12 are faulty. 3% of 400 is 12. So if 12 are faulty, 388 of the 400 are good. Now I'm going to pull a second one, and it needs to be good. Okay, none of them can be faulty, so the next one's got to be good. Well, there's 387 good ones left out of 399. So it's going to look like this. And that's all the work. These problems aren't long, it's just tricky to actually identify what you're supposed to be doing in each problem. So it's 1 minus, I'm going to do big parentheses, little parentheses, 388 divided by 400. Then another set of parentheses, 387 divided by 399. And I'm getting an answer of 0.0592. So this is the probability that we will be denied. There's about a 6% chance or so that we're going to be denied. Okay, and that problem right here is about as hard as this could possibly get, because there's a lot of little work we had to do, and you actually had to identify the fact that we're talking about 1 minus none. Okay, so to sum up this whole lesson, we are looking for, we've learned 2 new formulas, conditional, and at least one. We learned 2 new formulas, and we just are in every question trying to identify which one am I using right now. And that's it. All right, so